Welcome again. Today is 4th of February 2022 and time is 3 past 4 p.m. And you are welcome again. We continue with this topic, chemical, physical and biological changes in submerged soils. And in the last presentation, you have seen certain, this was the last slide in the last presentation where you have seen the stabilization of the soil pH at almost neutrality after submergence, and it has got several advantages for rice growth. Adverse effect of low or high pH per se are minimized. So if you have high pH, if you have low pH, these kind of pH will create problem for the plants. Plants will not have better growth. But in case of rice where fields are submerged, so such adverse effects are minimized. Excess of aluminum and manganese in acid soils are rendered harmless. So if your pH is too low in soil and there is no submergence, then this aluminum and manganese can be very, very toxic, very, very dangerous for crops. But if you submerge the soil, then pH will be raised, and this increased pH will reduce the aluminum and manganese toxicity. Similarly, iron toxicity will be increased if your soils are not basically very acidic. Availability of phosphorus, molybdenum, and silicon increased. I repeated it. And mineralization of organic nitrogen is favored. So mineralization of organic nitrogen is favored under anaerobic conditions. Can somebody throw light on this? What do you mean by mineralization of nitrogen? Organic nitrogen or simply nitrogen? What is mineralization of organic nitrogen? How it happens?
Conversion of organic to inorganic, an available form that can plan uptake.
Very good. So he's saying that conversion of organic nitrogen into inorganic nitrogen is mineralization of organic nitrogen. That is true, but that is very brief answer. I want some detailed answer. What happens in mineralization? How it starts and how it ends?
Sir.
Yeah.
Sir, in the aerobic soil, both bacteria and fungi help in the mineralization of organic nitrogen, and they take some part of nitrogen. Fungi, as compared to bacteria, take more nitrogen for their tissue buildup, and thus the mineralized nitrogen in case of fungi will be less. In waterlogged condition, fungi will not be there, actinomycetes will not be there, which take major part of their nitrogen in tissue buildup, and bacteria are present. And bacteria, as compared to fungi and actinomycetes, take lesser nitrogen in tissue buildup, so they will mineralize more nitrogen as compared to the tissue buildup nitrogen.
Excellent, excellent. But answer remains incomplete. What you said is correct, and thank you for that. But his question is that mineralization of organic nitrogen is favored. Favored.
Sir,
what does it mean? First thing, and what are the steps?
So nitrogen to ammonia is mineralization.
Ammonia is mineralization. Nitrogen is not found in free forms in soil, you know. Nitrogen, you mean N2 ammonia, N2 NH3. So it is not possible. Our nitrogen is complexed with other elements, or it is in organic form. If it is in inorganic form, it cannot stay alone. It cannot stay as N or N2. So,
Sir,
yeah.
Sir, organic matter at first undergone through or goes through hydrolysis, then it forms some amino acids or polypeptides. Then it goes through aminization, it forms amino acid. Then it gone through ammonification, means formation of ammonia. Then it goes through nitrification. Then it forms nitrite. Then again it oxidizes and forms nitrate. That is the available form of nitrogen for plant.
I wanted this answer actually. Others were also correct. But they could not get what I wanted to ask.
Sir, we joined, sir. Late, sir. What is the question? I don't know.
Why mineralization? He has told the steps of mineralization of organic nitrogen.
Yes,
it starts with protein and ends with nitrate. And then question comes, why mineralization of organic nitrogen is favored under submerged condition. Question is mineralization. It is a statement that mineralization of organic nitrogen is favored by submergence or by flooding. What does it mean?
Sir, reduction process will be easy for this
Reduction process,
due to
Sir,
unavailable of oxygen.
or I can say net mineralization. If I say net mineralization
Yes,
is
sir.
favored, then what does it mean? So answer is that it is not complete. All the steps are not complete, particularly when your nitrification, when your ammonification has happened. Ammonification will result in formation of
Ammonia.
of nitrogen
ammonia.
or ammonical form. And this ammonical form nitrogen will not be oxidized because of lack of oxygen. Because of lack of oxygen, that step will not take place in reduced zone.
Yes, sir.
And therefore, this ammonium accumulation will happen. Ammonium accumulation will happen. And also in the oxidized layer, wherever some aerobic organism are there, they will eat the oxygen of oxidized material, and nitrogen will be you can say denitrified there also. And also in reduced zone, if some nitrate from oxidized layer leaches down, some oxygen leaches down, then that nitrate will be immediately converted to N2. That is your denitrification. So overall net gain is there. Under submerged condition, net gain of nitrogen is there compared to aerobic setting. So that is the message. So overall, you can say that submergence increases nitrogen availability. One statement, if you remember, that submergence means flooding the soil increases nitrogen availability. That answer is true. Phosphorus availability, how this phosphorus availability is increased, we will see. How molybdenum or silicon availability are increased, we will see. But at the same time, if your pH is raised in acidic soil, then you will not require lime. Liming is not required. Another point is that iron toxicity in acid soil is lessened due to flooding, because in acid soils, iron toxicity is quite common in acid soils. These are lateritic soil found in coastal areas in India, also in Kerala and some other parts. You will find acidic soils, and these soils you can find some iron toxicity. But flooding, if you go for flooding, then pH will increase and iron toxicity will be lessened. Now you have any point of discussion? If not, we move forward. Now, just now you have seen that iron toxicity is an issue in rice. So iron toxicity, when you expect iron toxicity, so it is affected by basic soil pH. If your soils are too acidic, then you will have more iron toxicity. Clay content, higher the clay content, what is relation of clay content and this iron toxicity? More toxicity.
Directly proportional.
Yeah, higher the clay content, more iron toxicity. Organic, we will discuss it. Organic matter content increases iron toxicity. Soil type, just your clay content is also soil type. And soil temperature also affects iron toxicity. We'll see it now. So what happens after submergence of a soil? Fe3 oxide hydrates are reduced to Fe2 compounds. This is number one. So ferric is not toxic, but ferrous is toxic because it is soluble and it is available to the rice crop. The concentration of water-soluble iron may vary from 0.1, very small, ppm shortly after submergence to as high as 600 ppm. Water-soluble means available iron, that is Fe2. In acid sulfate soils, which are there in Kerala, the concentration may be as high as 5,000 ppm, which could be very, very toxic within a few weeks after submergence. So this iron toxicity can happen. iron toxicity. When can you call a soil iron, that in this soil iron toxicity will happen? What are the levels of iron that will result in toxicity of iron to the rice crop? So it varies. The toxicity levels varies with the soil, with the temperature, with the climate, with the plant also, with the variety also. So soil iron content ranging from 20 to 5,000 milligram per kg. This is in ppm. This is for soil. In soil, iron toxicity can happen at 20 and can happen between 20 and 5,000 milligram per kg, depending upon the soil, plant, and climatic conditions or differences. And iron leaf concentration from 300 to 2,000 milligram per kg or ppm from 2 weeks after rice transplanting to the late reproductive phase. So you have critical levels for toxicity here, which have very wide range. Now, this range has come down now because a lot of people have done work on this and there are different data. The data I am reproducing here are the most acceptable and most common values. So iron toxicity in rice continues. Iron concentration, that is Fe2 plus in soil solution is 250 to 500 milligram per kg due to reduced condition under prolonged submergence. Means the toxicity of iron will happen to the plants if soil contains 250 to 500 milligram per kg of Fe2 plus. One more work by Lantin, a soil solution concentration of 300 milligram water soluble iron per liter is generally considered the critical limit for cultivation of lowland rice. So he says that up to 300 ppm level, there is no problem. But if iron concentration increases beyond 300 ppm, then it will become toxic to the rice. So you can remember, considering all these points, that 250 ppm. If you have 250 ppm or more iron in soil, available iron in soil, then toxicity can be experienced. Now, question is why this range is given? Because this will depend upon, for some cases, it may be 450, for some cases, it can be 255 and like that. Because the tolerance of varieties are different and the kind of soils, climatic conditions, all will affect the toxicity of iron. Even percolation rate from the soil. Now you see this. So it can be only ferrous iron, which is toxic in general, and ferrous iron concentration after submergence is positively correlated with clay and organic matter. That means iron toxicity is correlated to clay. Higher the clay concentration in soil, more is the toxicity of iron. Higher the organic matter, more is the toxicity of iron. Nature and content of the ferric oxide hydrates, pH of the soil and temperature. There can be variety of hydrates of ferric oxides. So some may cause more acidity, some may cause less acidity, and some may be broken very easily, some may not be hydrolyzed easily. So these nature of these oxides hydrate will also decide the toxicity, pH of the soil and temperature. So you can see strongly acid soils with adequate organic matter and reactive iron oxides can build up toxic concentration of Fe2, reactive iron oxides, and cause iron toxicity in submerged altisols, oxysols, and acid sulfate soils in tropics. So these are the soils one can experience more iron toxicity. Now you see very interesting picture looking to be complicated, but I will try to simplify it. This picture shows you how toxicity of iron happens in the plant. If your iron, ferrous iron is accumulated in large amount, it is at toxicity level, say 300 ppm, then it is absorbed by the plants. It is absorbed by the plant, then how it is doing the damage to the plant, how it is it has become toxic to the plant. So this picture tells you little bit biochemistry or physiology, that what is what harm this iron is doing to the rice plant. So before that, you need to know two things. One is Fenton reaction, other is ROS. So these two terms you need to understand. Fenton reaction means it was described first time by Fenton, who observed the oxidation of tartaric. Tartaric acid is a kind of organic acid which is produced in plant cells. So who observed that the oxidation of tartaric acid by hydrogen peroxide, H2O2, hydrogen peroxide, is a ROS, reactive form of oxygen. So hydrogen peroxide in the presence of ferrous iron. So ferrous iron act as a catalyst, and then this tartaric acid can be oxidized by hydrogen peroxide. Just for the time being, you try to understand what is Fenton reaction. Now, what is ROS? ROS is reactive oxygen species. Reactive oxygen species, which is more reactive than normal oxygen. Means oxidizing power of ROS is much higher than the simple oxygen. Reactive oxygen species. Highly reactive chemical molecules formed due to electron receptivity of oxygen. For example, means they are made by oxygen. For example, peroxides, superoxides, hydroxyl radical, singlet oxygen, or alpha oxygen. So these are different forms of reactive oxygen. Now you are seeing in this picture, this ferric can be converted to ferrous in the reduced zone, and in oxidized zone, wherever you have oxygen, this ferric form is present. Now you see on your right side, there is a flow diagram having several arrows, and you start from the bottom. Just concentrate your eyes on the bottom of this flow diagram. Large concentration of Fe2 in submerged acidic soils. If you have submerged acidic soil and you can find large accumulation of ferrous iron, then what happens? This ferrous uptake by the plant root. This ferrous is taken by the plant root and it is distributed in different parts of the plant. Then now the iron is overloaded in plant tissues. Too much iron everywhere. In every cell you will have lot of iron. What happens here? The Fenton reaction happens. Fenton reaction, you know. So what will be the result of Fenton reaction in the plant? Overproduction of reactive oxygen substances or species. And now once the reactive oxygen is produced, what it will do? It will damage the cells. It will damage the plant cells. It will damage the DNA. It will damage the proteins at cellular level. And then physiological disorders will happen and there will be change in color. It will reflect in the change in color, bronzing symptoms on leaves, and finally your crop growth, photosynthesis, or yield loss will happen. So this is how iron toxicity happens and what it is doing to the plant. It is reducing the growth of the crop and finally you will get less yield. So therefore iron toxicity is not a desirable thing. Now criteria for the iron toxicity hazard means where you can have more iron toxicity and when you can have less iron toxicity. So pH of the dry soil, I think you know how pH of the soil is estimated. You get the soil, air dry it, crush it, powder it, and take the pH. So that is your dry soil. So basically, if dry soil is having high pH, fundamentally the soil is having high pH or low pH. So low pH means fundamentally or basically, then you will have more iron toxicity. Amount of reserve acidity, higher the reserve acidity, higher is the iron toxicity. So reactivity and content of ferric oxide hydrates, we already covered it. Soil temperature means low temperature, less than 20 degrees centigrade may cause iron toxicity in soil. And if temperatures are somewhere around 25 to 35 degrees centigrade, so toxic high concentration are short-lived. Means ultimately, you will not have high toxicity of iron in rice. Soil organic matter content, more organic matter in acidic soil, more iron toxicity. Higher percolation rate, less iron toxicity. Interflow from adjacent area, less iron toxicity because they will dilute the iron concentration. So this is how these are the factors which can affect the toxicity hazard. Now you see, try to understand this picture, very interesting picture. This iron toxicity shows you the pH, and I think you may not be able to see this picture, what is written there. So on x-axis, you have weeks after submergence. On y-axis, you have iron activity, means the availability of iron, the concentration of available iron. You can see on x-axis, y-axis, ppm iron. So you can see they have tested in different kind of soil, and you can see the pH and organic matter. Just I read for you. If pH of the soil is 4.6 and organic matter content is 4.1, then iron activity of iron or concentration of iron in soil, that is ferrous iron or available iron, is 2.78%. The levels are very high. If your pH is 4.6 and organic matter is 4.1%, the iron activity is 2.7%. If you increase the pH to 5.3, but reduce the organic matter content at the same time, 2.5% organic matter, just to half the organic matter, then you will have just 0.91% iron activity. Similarly, if you further increase the pH to 5.5, but also increase the organic matter to 4.2, then you will have high activity of iron. Then next, if you increase the pH to 6.6 and organic matter just 2%, then iron activity is very less, just 1.6%. And if pH is 7.6 alkaline pH and organic matter is 1.5%, then you have active iron just 0.3%. So from this data support that lower the pH, more iron toxicity. At lower pH, if you increase organic matter content, the activity of iron toxicity increases. You go on increasing the organic matter, decreasing the organic matter content and increasing the pH, it will reduce the iron toxicity. So this is how organic matter and pH are related to iron toxicity. How iron toxicity is reduced on submergence. So what happens when you submerge the soil, and with the passage of time, the soil pH will automatically increase, and then your iron toxicity will decrease. So the concentration of ferrous iron in the soil is very sensitive to pH changes. Increase of 1 unit of pH from 6.25 to 7.25 decreases ferrous iron concentration by 100 times. So you can see the value of iron concentration Fe2 plus in ppm. At 6.25, it is 1114, means 1114. But at 7.25, you see value just 11. So 11, if you multiply it by 100, then you will get 1100. So that is why this 100 times. So the message is simple. If you increase the pH of the soil, iron toxicity decreases. And as you already know that flooding can increase the pH of the soil. So therefore, the iron toxicity may be there for the brief period, shorter period. Now, so iron is over. Now we switch over to manganese. You also learned that manganese availability also increases in submergence. Due to submergence or flooding, manganese availability also more. Why it is more? First thing is the reduction of the oxide of manganese. So Mn4 is reduced to Mn2. Reduction may result from these compounds functioning. Electron acceptors in the respiration of microbes. This manganese is used as an electron acceptor in the respiration of microbes. You can remember this statement, manganese is compulsory. Chemical oxidants of reduction products. Manganese fall to more soluble form due to anaerobic metabolism of soil bacteria. So it is a biological process also. Manganese is more readily reduced and rendered soluble than iron. Release of manganese into soil solution precedes that of iron. So overall, you can see the manganese availability also increases due to flooding. And in some cases, it can also go to the level of, go to the toxic level. I'm not touching that part. Now, just we discussed about the why nitrogen availability is more in flooded soils. You have seen the mineralization, etc. Just we discussed. So conversion of organic nitrogen to inorganic nitrogen, it stops at the ammonium stage. You know, I told ammonification, production of ammonium is there. Then lack of oxygen, your nitrification cannot happen and ammonium is accumulated in the soil. So though organic matter mineralizes slowly in anaerobic than in aerobic soil, but the net amount mineralized is greater because less nitrogen is immobilized. Another important aspect is that less nitrogen is immobilized because of bacteria. There are no aerobic bacteria or large population of bacteria to immobilize this mineralized nitrogen. So that is also one of the reasons. The availability of nitrogen in flooded soils increases with increases in nitrogen content, pH, temperature, and duration of previous desiccation of the soil. The availability of nitrogen in flooded soils increases with increases in N content. If you increase the nitrogen content, the availability increases, and similarly pH, temperature, and duration of previous desiccation period. Now, there was a statement that phosphorus availability increases upon flooding. So if you remember in soil fertility, if you apply phosphorus, it is suggested if you are applying nutrients based upon cropping system, suppose rice wheat cropping system. So in that case, you do not have sufficient phosphorus to apply. Then phosphorus should be applied to wheat crop, not to the rice crop. But so far zinc is concerned, then zinc should be applied to rice crop, not to the wheat crop on cropping system. So that means in case of phosphorus, even if you do not apply phosphorus and your soil was rich in phosphorus, so that phosphorus can be easily made available to the rice crop. So you don't need to apply phosphorus under those conditions. So because phosphorus availability increases on flooding, if you are having continuous submergence, that phosphorus availability is more. So mainly due to reduction of ferric phosphate to ferrous phosphate. So conversion of ferric phosphate to ferrous phosphate increases phosphorus availability. Number 2, hydrolysis of aluminum phosphate increases its availability. Number 3, dissolution of calcium phosphate, because calcium phosphate may be there in alkaline soils. It results from the accumulation of carbon dioxide or acidification of the alkaline soil. So under both conditions, whether it is alkaline soil or acidic soil, submergence results in the increased availability of phosphorus. For details, those who are interested to know more details on this subject, they can contact me. Now, similarly, silicon availability is more in flooded soil because the concentration of silicon in soil solutions increases slightly after flooding and then decreases gradually. Means in the beginning, it reaches a very high level, and then after that, it decreases gradually, but it remains more than the original level. Release of silicon following reduction of hydrous oxide of iron, sorbing silicon and to the action of carbon dioxide on aluminosilicates. So for the time being, you can just remember that flooding results in increased availability of silicon, because silicon is not a necessary nutrient, essential nutrient for rice, but it is beneficial nutrient for rice. It gives strength to the straw. It makes rice crop tolerate the lodging. It makes rice crop lodging resistant, and it invites less infestation of insect pests and disease. Sufficient silicon nutrition results in reduced incidence of paddy blast. Rice blast is a disease. If your soil is rich in silicon or you apply it from outside, then it can prevent the invasion of the fungus, and it can reduce the paddy blast. Now, molybdenum availability is also increasing due to flooding. Concentration of water-soluble molybdenum in soil increases after flooding, presumably as a result of desorption following reduction of ferric oxide. I think you know what is desorption, what is absorption, what is adsorption, and so on. Now, more emphasis on zinc. Why water-soluble zinc availability decreases upon flooding? Many of you might be knowing that deficiency of zinc was first time discovered in rice, Khera disease due to zinc deficiency. And since then, people have in mind that this submergence results in a reduced availability of zinc. That is true also. So if you have more water in soil, you will have more zinc deficiency. If you drain out water from the soil, your zinc availability will increase. So therefore, in wheat crop, maize crop, issue of zinc deficiency is not that common as in case of rice. For detail, you can read the review that is very excellent review for more knowledge, zinc availability and dynamics in the transition from flooded to aerobic rice cultivation. So this is reference. Why water-soluble zinc availability decreases upon flooding? The decreased zinc concentration may be due to, these are the reasons. Number one, precipitation of zinc hydroxide as a result of increased pH after flooding. You know, after flooding, pH increases, goes up. So because of that, this precipitation happens in case of zinc. So zinc makes zinc hydroxide, which is not a available form. Similarly, precipitation of zinc carbonate due to carbon dioxide accumulation resulting from organic matter decomposition. So some carbon dioxide may be there by microbes or by organic matter decomposition, and it makes your zinc carbonate. So formation of zinc carbonate, zinc sulfide, or zinc hydroxide results in reduced availability of zinc. And high manganese concentration antagonize zinc absorption and translocation. So up to some extent, due to flooding, you just few slides back, you have known that manganese, increased concentration of manganese or increased availability of manganese. So that will precipitate some of the, or antagonize the activity of the zinc. So that also reduces the zinc availability. So chemistry of copper in flooded soil is similar to zinc. So both copper and zinc availability reduces due to flooding. Now, in brief, in submerged soils, chemical compounds are reduced during respiration of anaerobic microorganisms. Compounds are reduced in order, this is just summary of the things we discussed, based on the amount of energy needed. Nitrate is first because the least energy is required. You have seen they decompose or reduce in a chronological order. Reduction process causes a shift in the chemical compounds. Change in chemical compound result in other changes as soil color changes, soil pH changes, and availability of nutrients. You have seen many cases availability increased, only two nutrients, that is copper and zinc availability decreased. And now you see the physical effects of submergence or flooding. Puddling the soil, almost everybody knows is what is puddling. Mixing of saturated soil to create a watertight layer. When puddling is performed, it is a standard land preparation activity for rice produced in a flooded field or paddy, rice paddies. Why it is done? What is the purpose of puddling? The main purpose is to reduce the downward flow of water, percolation. So less water is needed to keep the paddy submerged. How it is done? By a draft animal or tractor, by machine. You have a puddler, you can do the puddling or churning of the soil by plow, by harrow, by cultivator, by any implement, you can do it. Now, what is puddling actually? So puddling, puddle means a clay. Puddle means a clay that can be worked to a water impermeable stage. That can be worked means that can be mixed, that can be plowed to a water impermeable stage. So that will be called as puddle. Means kind of gara, you know, kind of gara, making gara. Gara is your puddle. Puddling is the mechanical reduction in the apparent specific volume of soil. So this kind of definition can be given by a soil physicist, a physics scientist or soil physics scientist. He will say, okay, puddling is the mechanical reduction in the apparent specific volume of soil. Agronomists will say you keep the water standing in the field or flooded and then plow the land, and this is known as puddling. But soil physicists will say like this. And puddling results in the destruction of 91 to 100% macropores. I think you understand macropore, mesopore, micropores, and restrict the porosity. So continue with the puddling. We explain, you could follow the meaning of puddle and puddling. And we know it destroys the most of the macropores and restrict the porosity. Marked reduction in air-filled pore volume. Air-filled pore volume, just somebody was saying, and lowering of permeability because of destruction of macropore, mainly destruction of macropores. Now puddling continues. So what are other aspects of puddling? Lowering of resistance to raindrops, lowering of resistance to raindrops, and increase in deformability. Suppose there is rainfall, so it will not resist, soil will not resist. Rainfall will means have more impact on soil. It will have more impact on soil and increase in deformability. It will further deform the soil. Increase in microporosity, definitely decrease in macroporosity, but increase in microporosity causes an increase in water holding capacity. Impermeable layers of plow pans attributed to physical compaction and to elevation of clays. We discussed it. Elevation means leaching of clays and reduced iron and manganese. So because of this, impermeable layer is created. Then high bulk density of soil below the plow layer after wet tillage result in less downward flow of water and less leaching of nutrients. Now, other advantages of puddling are improved weed control by primary and secondary tillage through puddling, ease of transplanting, establishment of a reduced soil condition which improves soil fertility. Because of this impervious layer, water will stay for a long time. So you will have submergence of water, more submergence of water due to puddling. Reduced draft requirement. Draft means power, animal power, or any kind of power requirement for primary and secondary tillage. So initially, once you have done the plowing under dry condition, if you are doing the same, so reduce draft requirement for primary and secondary tillage, reduce percolation losses. So overall, you can see advantages of puddling. Now, just forget the puddling. Now, if you submerge the soil, if you flood the soil and water remains continuously flooded on the soil, so what it is going to do? What just submergence alone can do to the physics of soil? What kind of physical changes can be made by the water, standing water on the soil? So following influences can be made by the flooded water. Standing water controls weeds and eliminates water stress. So if there is continuous flooding, then water stress will never be there on the plant. Here, water stress normally means excess water and less water or drought condition, means too much or too little is your stress. But rice does not do not mind this excess water. Rather, it is happy. But for other crops, excess water stress could be there, or low water stress can be there. So water stress is in both sense, excess water and less water. The depth has no effect on yield provided if less than 10 centimeter. Means up to 10 centimeter, no problem. You can keep 5 centimeter, you can keep 1 centimeter, you can keep 9 centimeter. But if you take it beyond 10 centimeter, continuous flooding, then yield and growth will be affected. But if it is less than 10, then it is not going to affect the yield adversely. Evaporation leads to deposition of insoluble carbonates. Because of evaporation, I think you might be knowing that evaporation leads to deposition of insoluble carbonates, water-soluble salts and silica, causing buildup of salt, alkalinity, and high boron concentration, particularly under shallow water conditions or in canal irrigated areas. Irrigation water can provide potassium and sulfur. This is quite interesting. This is another indirect benefit of flooding. Means every time you are applying water, and suppose that water contains potassium and sulfur, then it will add to the nutrition of the rice crop. So that way means it is flooding is giving you nutrients, assuming 1 meter water per crop and 1 ppm of an element compounds to 10 kg per hectare. So there are some places in India where river water or canal water is rich in potassium. In Karnataka, there is some place where you got some river is there. I missed the name. If any student knows, kindly share it. That river contain very good quantities of potassium in water. So that way means potassium requirement is partly met. Does anybody know about that river which is giving very good potassium in water?
Sir, Krishna River, sir.
Krishna River. I'm not sure, but there is some information. So message here is that some water may contain some potassium and you are repeatedly applying water. You need to apply more and more water. So the indirect benefit is that addition of certain nutrients. Drastically retards gas exchange between soil and air. Stabilizes soil temperature. Stabilizes soil temperature. This is interesting. How this flooding can stabilize temperature? Can anyone throw his or her idea? How this flooding can control the temperature? Stabilize.
Sir,
Normal.
the specific heat of water is 5 times the specific heat of soil. So if the soil is flooded, then it will take more calories or the more energy to raise the temperature. So it will stabilize the soil temperature.
Like what could be in other way when it is high outside? So there can be two extreme. One can be lower side, one can be higher side. Because,
in case of higher side, the latent heat will also be an option.
Yeah. So I think you got some idea how this water has some cooling effect and warming effect. So it has both kind of effect, cooling effect and warming effect. So that way it will benefit the rice plant. So this is also a kind of physical change because it is happening in water, and this water is helping the crop. Causes swelling of colloids. So colloids will swollen. So because of this water and this water, colloids get swollen. Destroys aggregates. Soil aggregates are destroyed because of compaction, because of pressure of water, and reduces permeability. So these are some physical changes in flooded soils. Now we see in detail what are more physical changes in flooded soils. Retardation of gas exchange. So you know a lot of gas exchange happen between the soil and the atmosphere. But you have in between soil and atmosphere, you have a water layer. So this water layer controls or affects the exchange of gases from soil to atmosphere and back from atmosphere to soil. So how oxygen is affected? Retardation of gas exchange. Oxygen deficiency happens in soil. The moment of a soil is flooded, its oxygen supply is virtually cut off. Oxygen can enter the soil only by molecular diffusion in the interstitial water. The process is 10 times slower than in gas-filled pores. So the process is very slower. I think you remember, parenchymatous tissues. Oxygen diffusion rate suddenly decreases when a soil reaches saturation by water. So then it slows down. Within a few hours of flooding, microbes use up the oxygen present in the water or trapped in the soil and render a submerged soil practically devoid of molecular oxygen. So ultimately, finally, after a few days, you will get very, very low quantity of oxygen in soil. A flooded soil, however, is not uniformly devoid of oxygen. The oxygen concentration may be high in surface layer. If you remember, oxidized layer will have some quantity of oxygen. However, in reduced zone, only root area can have oxygen, but some other site can also have. Maybe if you go to the soil bed or on the bottom and go further, then you can find some oxygen inside the lower layers of the soil. The oxygen concentration may be high in the surface layer, which is a few millimeters thick and in contact with oxygenated water. The thickness of layer represents a balance between diffusion from floodwater and oxygen consumption by the soil. It increases in thickness as the crop matures with the passage of the time. Oxygen deficiency continues. Below the surface layer, the oxygen concentration drops abruptly to practically zero. Below the surface layer means your oxidized layer. The brown color of the oxygenated layer, its chemical properties and its oxidation reduction potential undergo a similar abrupt change with depth in submerged soils. If the root zone of rice is devoid of oxygen, how do rice seeds germinate? Now, question comes, if there is no oxygen during the seed germination, how the seed germinates and grow? And rice roots grow and accumulate nutrients without oxygen. That question comes. So sometimes you must have seen that if there is thin layer of water, the seed germinates. So rice can germinate at oxygen pressures of less than 3 millibars because of a highly developed system of anaerobic respiration. This is only for germination. So if the oxygen pressure is even less than 3 millibars, because of highly developed system of anaerobic respiration, rice can germinate. But growth is retarded and seedling establishment adversely affected at low oxygen. So at very low level of oxygen, seed can germinate, but the growth of the seedling will be adversely affected or it can die if oxygen supply is not increased. Rice roots, like the roots of dryland plants, need oxygen for growth and nutrient accumulation, and therefore for roots, no problem. The source of oxygen is gas. It can diffuse from the aerial parts through the parenchyma, and these parenchyma are continuous, starting from tip of the leaf to the root cap. They are continuous, these parenchymatous cells. So oxygen can travel from atmosphere to the roots via plant system. Now, first thing is that devoid of oxygen or less oxygen in the soil. Second point is accumulation of carbon dioxide. It will not be escaped through water to the atmosphere. It will be escaped. It will escape, but in less quantity, in very insignificant quantity. So most of carbon dioxide will be trapped in the soil. The presence of layer of water also drastically cuts down the escape of soil gases, not CO2. There may be some other gases also. So those will be stopped by some of them will be stopped by the water layer. Carbon dioxide, methane, hydrogen, and nitrogen produced in the soil tend to accumulate, build up pressure, and escape as bubbles. So once the pressure is built up, they can escape. Certain quantity of these gases can escape, but it is not that whatever is produced, the whole quantity will be escaping to the environment. Part of that will escape. The partial pressure of carbon dioxide in a soil increases after submergence and reaches a peak of 0.2 to 0.8 bars 1 to 3 weeks later. Carbon dioxide injury to rice may occur on acid soils, low in iron, organic soils, and cold soils. So carbon dioxide injury is possible under certain conditions. Stabilization of soil temperature. We just discussed, somebody told us the effect of flooding on soil temperature follow from 3 important thermal properties of water. You might be knowing it: high specific heat, high latent heat of vaporization, and higher thermal conductivity than soil material. So because of this, the high specific heats prevent violent temperature fluctuation. The high heat of vaporization tends to keep flooded soils cooler than dry soils. So therefore, temperature is normalized or stabilized. In some rice production areas, modification of soil temperature is an important benefit. Soil and water respond differently to changes in air temperature. Submerging the soil keeps soil cooler when high temperature injury may be a problem, helps reduce low temperature injury at night in cooler climates. So this is kind of summary of stabilization of soil temperature. Benefit of submergence. So now you must be realizing that how many benefit this puddling and this flooding is having for the rice crop. Now you can realize. And many times you will see people will be talking about aerobic rice, direct seeded rice, this rice and that rice. So practically, when we go for practice, then things are different, my dear students. Things are altogether different. So if you do not have very good management under direct seeded rice or aerobic rice, you will not get good yields. It is not possible. But in if you have flooding, and other management practices are just normal. So you can derive several benefits of flooding for your rice crop. So it is easier to say that rice consumes too much of water, and we should go for other methods. Of course, methods have some promise, but if you have good water supply, you should not miss it. You should grow rice by puddle transplanted method. These are my views. Swelling of colloids. So this is another physical change due to flooding. So when a dry soil is flooded, soil colloids absorb water and swell. It is very simple. The rate of water absorption and volume increase of mineral soils depend on the clay content, type of clay, mineral, and the nature of adsorbed cations. So all these will have different properties. Minerals or clay content, they will affect the water absorption differently. Swelling is usually complete in 1 to 3 days. First 1 to 3 days, the higher the clay content, the greater the swelling. The expanding lattice type clays, you have variety of clays, Montmorillonite and so on, swell more than the fixed lattice type, kaolinite and halloysite. So type of clays are important. Sodium clays swell more than the calcium and potassium clays. When a puddle soil is dried, it shrinks and the decrease in volume equals the volume of water lost. So deep cracks are common in puddled rice field after draining and drying. So they cause heavy loss of water by percolation during reflooding. So that is what in water management, when we deal with water management in rice, it is never permissible to allow formation of cracks. Formation of cracks should not be allowed in transplanted puddled rice. If cracks are formed, then water requirement will suddenly increase because water can easily percolate through these deep cracks, and it takes a long time to fill these cracks by swelling and other action of the clay minerals. So better to avoid formation of cracks in the rice soils during the growth of the rice crop. They cause heavy loss of water by percolation, these cracks. Consistency. Consistency is another physical property of the soil. As the moisture content of a soil increases, the cohesion of water films around soil particles causes them to stick together. I hope that you understand the certain physical properties of soils like consistency, adhesion, cohesion, and all these, and plasticity, etc. So causes them to stick together, rendering the soil plastic. If you really do not know, there is no shame in learning anything. You can learn anything at any age, any stage. We should not be shy. So what you can do, take Brady's book, Nature and Properties of Soil, and I advise you, whosoever, whether you are from water science and technology or soil science or agronomy or soil physics, whatever discipline you have, you should try to read book of Brady, Nature and Properties of Soil, from page 1 to page last. It will help you in many, many courses, many subjects. If you are in soil science or agronomy or water science, technology or physics. So please read. So all these things, simple things are very well discussed, very nicely discussed in that book, so that anyone can understand very easily without help of a tutor or a teacher. You can follow that book. I recommend you must read that book. So consistency.
Sir, foreign writer books is hello.
Yeah.
No, sir, my foreign writer books is so hard, sir.
Not hard to understand or hard to read, or hard to means what in what sense you are saying hard? See, tell me, I love my country, I love my people, I love my scientists, I love everything. But tell me one book of soil science which is as popular as Nature and Properties of Soil from India. I'm not against India or against my own country, but we could not write a book of that class, that level, I can tell you. If anybody knows any book which is better than, I will not mind it. It has nothing. It is just off the record discussion. Can you tell me any book on soil science as per content wise in that area, written by nature, written as in Nature and Properties of Soil? Can you tell me any one book? So to be honest, I need to be honest with the students. I tell you what Indian authors are doing to write books, particularly in this case, all the books on soil science, they get inspiration from Nature and Properties of Soil. In many books, this is just copy and paste from Brady's book, from Nature and Properties of Soil. So I don't know, I will not force you to agree to my point of view, but these are the things. So there is no harm. You can try. Maybe one time you will fail to understand, but next time, suppose you don't understand any term, go to Google immediately. If you don't follow any meaning of anything, suppose I am teaching you this consistency. So just you type flooding and consistency, soil flooding and consistency, and just write rice. You will get answer. You will get a simplest answer. So thing is that you have to learn yourself. Teacher will not be there. Teacher will not teach you all the subject, all the things. It is not possible. So teacher can just put some spark in you, give you some spark in you so that you can run your car. So it is you who have to learn yourself. So keep your Google open, and anything which you don't know, just type in Google, you will get immediate answer, so that your studies will not be disturbed. Now, consistency, as the moisture content of a soil increases, the cohesion of water, at this moisture content, soils are easily puddled. At higher moisture content, as in flooded soils, cohesion decreases rapidly, making tillage easy. So why tillage become easy? Because of cohesion. But penetration increases and soil strength decreases. So if you increase penetration, then you will need more energy, more draft, rendering the use of heavy machinery impractical on flooded soils. So that is another issue. Destruction of soil aggregates due to flooding. When a dry soil is flooded, the aggregates become saturated with water, and during the process, internal air pressure disrupts the aggregates. So there is breakdown of soil aggregates. Soil aggregates are important. So many times these paddy soils are blamed that soil breakdown of aggregates. But after some time, when you drain out, there will be formation of aggregate back in the soil. So swelling of colloids and dissolution of cementing agents such as iron oxide further decrease aggregate stability. Sodic soils show marked aggregate breakdown on flooding, whereas soils high in iron and aluminum oxides and organic matter suffer little aggregate destruction. So on soil drying and oxidation, a re-aggregation occurs. Reduction of permeability. Permeability, that is the purpose of flooding. So permeability is reduced, percolation is reduced. And submergence and availability of water. So this is a good sign that your crop will never have any stress, whatever stage may be. But if your soil is flooded with water, so there will not be any water stress. Weed competition is reduced because of submergence. And finally, you can see the puddling submergence. And puddling is a standard field practice for submerged rice fields. One reason it is used to slow the downward flow of water. Following physical benefits result from submerging soil for rice production. It helps reduce water stress during critical growth stages. It can be minimize plant injury from extreme temperature. Effective way to manage some weeds. So a number of things. So this finishes this topic. And now you can have your questions. And I can stop recording also.